One simple property of definite integration is that we can swap the limits of integration by introducing a minus sign. Okay, so this is actually a simple consequence of integration by substitution when we change the limits. So let me show you how that works. If I start with this and then I make a substitution, let y equal a plus b, in other words the sum of the limits, minus x, then I have dy equals minus dx. And then if I put that in here and evaluate y of a, you can see that y of a would be equal to a plus b minus a, so that's b. And likewise, y of b would be equal to a. So I've managed to swap the limits with this substitution, and I've brought in a minus sign coming from here. So I can write that then as b, a, with a minus sign, f of y dy. Well, that is equivalent to the right-hand side here, because y and x are what are called dummy variables. In other words, when we take the definite integral, they disappear. So in fact, we can call them any letter we like. So this is equal to this. If the function that we're integrating has a symmetry, then definite integration can be much simpler than it first appears. And there are two cases to consider. The first is of even functions where the function has a reflection symmetry in the y-axis. So in other words, the point here is equal to the point here. And in other words, again, f of x is equal to f of minus x. That's the first case. And the second case is odd functions where there's an anti-symmetry on reflection. So that is, the point here is equal to minus the point here. So we can write f of minus x is minus f of x. Well, in these two cases, we get simplifications. And you can see them just by looking at the pictures. In the even case, you can see that the integral from here to here is the same as the integral from here to here. So in other words, the full integral is equal to twice the integral from here to here. And you can look at the notes for an algebraic way to show that. Well, I'm going to look at the second case, the odd case, and you can see from the picture that the integral from here to here is opposite to the integral from here to here. So in other words, this will cancel with this. So we're expecting this to be 0. But how does that work algebraically? Well, we can split the definite integral into two bits, the first half and the second half. So I write that like this. And then I can operate on this. I can introduce a new variable. Let's say, let y equal minus x. Then I have dy equals minus dx. So I can put that in here, bring out the minus sign, and then I have integral from a to 0, remembering to change the limits, of f of minus y dy. Now here we can use the odd property to replace f of minus y with minus f of y, and that cancels out the minus sign. So we're left with a to 0 of fy dy. But the final step then is to flip the limits of integration, to switch them over, and that introduces another minus sign, so that we have the integral from 0 to a of f of y dy as the first term. And you can see that this will now cancel with the second term. At first glance, they're not the same because here we have x and here we have y, but we should remember that these are what are called dummy variables, because at the end of the day, in a definite integral, they disappear. They're integrated out. So this is equal to minus this, so the final result is 0, as we expect from the picture. A theme of this course has been that differentiation and integration are two sides of the same coin. More than that, they're inverse processes, so the action of one undoes the other. Well, that idea is encapsulated in these two equations. The first one tells us about the integral of a derivative, and the second equation tells us about the derivative of an integral. Well, hopefully the first one is very familiar by now. It goes to the heart of what we mean by integration, and we proved this result more carefully in a different clip. But when we think about the derivative of an integral, we have an expression which is maybe less familiar to you. Let's take a look at this now. So here we're taking the derivative with respect to x, and x appears in the limits. Well, in this case, it appears in the upper limit. Here, a is a constant. Y here is the variable of integration, also known as a dummy variable. It's called a dummy variable because you can see that the right-hand side should have no reference to y. It integrates out. Okay, so this expression tells us that the derivative with respect to x, when x is in the upper limit, gives us the integrand evaluated at x. And a corollary of this is that if we were going, let's say, from x to b, where b is greater than x, we would pick up minus f evaluated at x. Okay. So this is great. And these kind of relations together make up something called the fundamental theorem of calculus. So that tells you just how important they are. Okay, well, let's think a little bit more. Is there a generalization of this expression? What about if I were to think of a derivative of an integral where there were functions of x appearing in the lower limit and the upper limit? Okay, these could be arbitrary functions, let's say x cubed and x to the 5 or something like this. What now is the relevant expression? Well, we can take some steps to derive it. Okay, so if we let f prime equal little f, so capital F is the indefinite integral of little f, then we can evaluate this integral like so. Okay, so I can write out those two terms, and we've got f, the derivative of f evaluated at h of x, minus f evaluated at g of x, where these are the functions in our lower limit and upper limit. Well, what we have here is an example of the chain rule. We have a function of x. So we want to differentiate with respect to x a function of a function. So here we can use what we know from differentiation. We can say that this would be given by dh dx times by f prime evaluated at hx. And likewise, this would be dg dx evaluated at f prime gx, like so. Well, what do I mean by f prime? I mean this function, the derivative of this function with respect to its argument. Well, that's precisely this here. So in fact, this bit here is the integrand itself. So I'm going to write this like this. H prime f of h of x minus g prime f of g of x. This is now a general result for the derivative of an integral where functions of x are appearing in the limits. Okay, this means a derivative with respect to x. Okay, and it's the integrand at the upper limit and the lower limit that appear here, but we also need to account for the rate at which x is changing, i.e. that's how the derivatives come in. So let's just check that this equation is consistent with what I wrote here. Well, if I make h of x just x, set h of x equal to x, then its derivative is 1, and I have f of x. Okay, and if I set g of x equal to a constant, so the lower limit equal to a constant, then the derivative is 0. So we lose this term, and then we would just get back f of x, this. Conversely, if we set h of x equal to a constant, then we lose this term, and if we set g of x equal to x, then we pick up this term here, and we've got a minus sign, as is obvious there, so we get back to this. So yes, this is consistent with this, but this is a more general formula.